Hello guys, this is OBC from Special Maths Academy. In this video, we're going to be solving question 4 of 2022 Junior Maths Olympiad second round. We're told that x, y, and z are three real numbers greater than 0, such that x plus y plus z is 1. And we're asked to prove that square root of 6x plus 1 plus square root of 6y plus 1 plus square root of 6z plus 1 is less than or equal to 3 root 3. In solving this question, we're going to make use of a claim and the claim we're going to make use of, right, is that 3 into a squared plus b squared plus c squared is greater than or equal to a plus b plus c squared. So you can prove this claim with Cauchy-Schwarz, but in this video we're going to be proving it with AMGM. So I'll just write down what the AMGM inequality is by this side, for in case there's someone that is new to it. So the most basic form of AMGM says that a squared plus b squared is greater than or equal to, the most basic form of AMGM says that a plus b is greater than or equal to 2 root ab, where a and b are real numbers greater than 0. Thus a and b are elements of real number and a and b are greater than 0. And so we'll come back here now to our question to prove this claim that we made here now. From the AMGM inequality, we know that a squared plus b squared, right? So this is the proof of the claim. A squared plus b squared is going to be greater than or equal to 2 times square root of a squared times b squared. So in this line that we wrote here now, we're just substituting a squared in place of a in this AMGM inequality here, AMGM, and we're substituting b squared in place of b in the AMGM inequality. Then when we simplify this, we get that a squared plus b squared is greater than or equal to 2 root a squared b squared, which is 2ab. So this is the first thing we get. And when we do something similar for a squared plus c squared, we get that a squared plus c squared is greater than or equal to 2 root a squared times c squared from AMGM inequality, and a squared plus c squared is greater than or equal to 2ac. And for b squared plus c squared, so we'll have something similar, 2 roots b squared times c squared. We have that b squared plus c squared is greater than or equal to 2bc. And so we're going to call this equation here equation 1. Sorry, this inequality here inequality 1, and then this second one here inequality 2, and this third one inequality 3. So when we add 1, 2, and 3, the three inequalities that we've gotten so far, right? So from 1, on the left hand side, we're going to have a squared plus b squared. From 2, we're going to have a squared plus c squared. And from 3, we're going to have b squared plus c squared. And on the right hand side, from 1, we're going to have that this is going to equal to 2ab plus 2ac from inequality 2, and 2bc plus from inequality 3. And then this is what we have. So let's go down a bit here. Awesome. And then when we simplify this further, we'll have that 2a squared plus 2b squared plus 2c squared is greater than or equal to 2ab plus 2ac plus 2bc. So what we're going to do now is that we're going to add a squared plus b squared plus c squared to both sides of the inequality. When we do that, we're going to have 2a squared plus 2b squared plus 2c squared plus a squared plus b squared plus c squared. And this is going to be greater than or equal to a squared plus b squared plus c squared plus 2ab plus 2ac plus 2bc, right? And then when we simplify the left hand side, you notice we have 2a squared, 2a and a squared, 2b squared and b squared, 2c squared and c squared. So when we join them together, right, we're going to have 3a squared plus 3b squared plus 3c squared on the left hand side. It's greater than or equal to the right hand side. And then the thing about this right hand side is that this is the expansion of a plus b plus c squared. So if you're not convinced, you can just expand this manually. You notice that this is what you get, right? So instead of writing this right hand side now, we're going to write it as a plus b plus c squared. And then when we factorize the left hand side, we're going to have 3 into a squared plus b squared plus c squared is greater than or equal to a plus b plus c squared. And then this is what we wanted to prove in the claim, right? That 3 into a squared plus b squared plus c squared is greater than or equal to a plus b plus c squared. Yeah. Then we're going to make use of this now in the question we're solving. So remember that in this problem we're asked to prove that square root of 6x plus 1 plus square root of 6y plus 1 plus square root of 6z plus 1 is less than or equal to 3 root 3. So we're going to substitute square root of 6x plus 1 for a. We're going to substitute square root of 6y plus 1 for b and square root of 6z plus 1 for c. Like based on this claim here, right? Since we know that this is true. Yeah. And then when we do that, we're going to have 3 into, let me write down the things we're substituting. So we're going to substitute a. So in place of a, we're going to be writing square root of 6x plus 1. In place of b, we're going to write square root of 6y plus 1. And in place of c, we're going to write square root of 6z plus 1. Yeah. And then when we make this substitution in this, let me just call this inequality 4, I think. Yes. So when we substitute these values of a, b, and c in inequality 4, we have that 3 into square root of 6x plus 1 squared plus square root of 6y plus 1 squared plus square root of 6z plus 1 squared. We have that this is greater than or equal to square root of 6x plus 1 plus square root of 6y plus 1 plus square root of 6z plus 1 raised to power 2. So we got this by just replacing a in this inequality. Is inequality 4 that we know is true with square root of 6x plus 1, replacing b and c with their corresponding values. Then when we simplify this is that here we have square root of 6x plus 1 squared. So the square root and the square kind of cancel each other, and same thing happens here and here too. Then when we simplify based on that, we have that 3 into square root of 6x plus 1 squared now becomes 6x plus 1 plus, for the second term, 6y plus 1 plus 6z plus 1. We know this is greater than or equal to square root of 6x plus 1 plus square root of 6y plus 1 plus square root of 6z plus 1 all squared. And then when we factorize the left hand side further, so we notice we have 6x1 and 6z here. We have that 3 into 6 into x plus y plus z plus 3 greater than or equal to square root of 6x plus 1 plus square root of 6y plus 1 plus square root of 6z plus 1 all squared. And then remember that in the question we were told that x plus y plus z is 1. So we're going to replace x plus y plus z here with 1. So then this becomes 6 times 1. So this is 3 into 6 plus 3 greater than or equal to square root of 6x plus 1 plus square root of 6y plus 1 plus square root of 6z plus 1 all squared. And then when we simplify the left hand side, we get that this is equal to 27. That's 3 times 9, 27. Then what we're going to do now is that we're going to take the square root of both sides of this equation. So we're going to take the square root of 27. We're going to take the square root of this other expression here squared. When we do that, we're going to have that square root of 27 is greater than or equal to square root of 6x plus 1 plus square root of 6y plus 1 plus square root of 6z plus 1. So since we're taking the square root, like that's why these two gets cancelled, something like that. And then square root of 27, we know that this is 3 root 3. And then when we rewrite this equation and like we just flip this inequality so it looks like what we have in the question. That's 6x plus 1 plus square root of 6y plus 1 plus square root of 6z plus 1 is less than or equal to 3 root 3, which is what we're asked to prove in the problem. So let me just recap on how we're able to solve this question. We started by proving a claim that 3 into a squared plus b squared plus c squared is greater than or equal to a plus b plus c squared. I mentioned earlier that you can prove this claim with the Cauchy-Schwarz inequality, but in this video, I decided to make use of the AMGM in proving this inequality here. And I read the AMGM here in case someone is new to it. This is the AMGM inequality, that whenever A and B are real numbers greater than 0, we have this inequality to be true. And then when we prove this claim, right, we made use of the AMGM in proving this claim. Yeah, this was the point where we were done with the claim, right? That's this equation 4 here. So at this point now, we use the AMGM inequality to show that the claim that we made earlier is true. And then since we now know that this claim is true, we made use of it in proving the problem that we had. So we substituted square root of 6x plus 1 in place of a in this equation 4 here, inequality 4 here that we know is true. And we substituted square root of 6y plus 1 in place of b here, and square root of 6z plus 1 in place of c here. And then when we made that substitution, we just kept on simplifying, and at the end, we came up to this line here, where we had 27 equals this expression on the right hand side, and then we took the square root, and at the end we now got that what we're looking for is true. So that's how we were able to solve question 4 of 2022 Junior Maths Olympiad second round.